Dear students, let us see another experiment in electricity in your subject physics in the section electricity. One last experiment. This is comparing two resistances using potentiometer, right. That is what the concept is. So, we have already done couple of experiments using potentiometer. We are very familiar with potentiometer. Remember the point I always say, if you are referring to any experiment, all the previous experiments within that section you should have studied, right. This is the 6th experiment I am doing within electricity. So, anybody who is referring to this must have cleared off the previous 5 experiments I have done. Otherwise, certain explanations I will not do it here because I have done that in the previous experiments. When I took potentiometer for the first time, I have spent a lot of time and explained the concepts of potentiometer. Now, I would not explain it. I would not explain what is voltage drop here, voltage slope here. I will not explain all that. So, make sure you refer to the previous experiments and then come to this. So, this is the potentiometer setup, right, a battery. If you want, you can have a rheostat as well, and there will be a switch as well. And then you have a separate circuit. Can you see here? Separate circuit. What is in the separate circuit? You have two resistances, that is what you want to compare, right. I want to get the ratio R1 over R2. Remember in the previous experiment we compared two batteries electromotive forces E1 over E2. Similar one we are going to compare the R1 R2, and then see when this switch is plugged in, the circuit will have current in it. There will be a current flow here. Then you will have a voltage drop here V1 and you will have a voltage drop here V2, right. Okay. Now, let me mark V1, V2 down there. This is the plus side. So, let me mark it as this V1, V2. Similarly, the potentiometer also on this direction the voltage drops. And can you see I have a two-way switch here, and this is the usual galvanometer and the safety resistance components. So, imagine when this two-way switch is connected to this side. So, basically this point is connected here and point D is going through the galvanometer for the equilibrium. So, you take the sliding contact, move it here and there and find the equilibrium point. When you find the equilibrium point, the V1 and let us say it is L1. So, I can say the V1 here will be K L1. K is the voltage slope per centimeter. How much voltage drops is what you call K. Similarly, when you take it here, point F is getting connected. That means point C is already connected here. Point F means V1 plus V2 is going to get the balancing point. V1 plus V2. K L1 plus L2. Not L1 plus L2, L2 only. L2 only, not L1 plus L2. Now, the new length is L2, right? New measurement is L2. But you are getting V1 and V2. V1 means it has to be IR1. IR1. So, IR1 is KL1. Here you can say IR1 plus IR2. Same current, right? There is no current leakage. I into R1 plus R2 will be KL2. So, you divide 2 by 1, you are going to have I and I cancel because same current, you did not make any changes in this circuit. R1 plus R2 over R1, K and K cancelled, L2 over L1. From this you can take, this is going to be 1 plus R2 over R1, L2 over L1. R2 over R1, that is what you call comparison between the resistances, L2 over L1 minus 1. Simple as that. Right. So, that is how we compare the two resistances. Now, if you want to go for a graphical method, what you can do, you can change. See, if you want to go for a graphical method, we need constant on the other side, right? So, look at this. We can say L1 equals so L2 equals 1 plus R2 over R1 into L1. You can take this y, take this x, the whole bracket will be m. So, from the gradient, if you subtract 1, you will get the ratio between R2 and R1. But how do we get different L1, L2 values? You can change. This is going to be a variable resistor box. Change this resistance so that current changes. But when the current changes, voltage 1 will change. If voltage 1 changes, L1 will change. Right. So, first keep it at one point, get V1, V2, get L1, L2 readings, complete one set of readings. Then change the resistance, again take L1, L2, second set of readings. Change the resistance, keep it at that level, again L1, L2. Likewise, you can get 5 different sets of L1 and L2 values. You can draw the graph and then this will give you the gradient. From the gradient, you can get the ratio. Clear? This is what we call comparing two resistances using potentiometer. Quite straightforward. It's somewhat similar to the previous one where we have compared the two batteries' electromotive forces. More or less a similar one it is. Same current will flow through the battery E and resistances R1 and R2 in the external circuit. Therefore, the voltage drop across those resistors will be in the proportion of their resistances. Correct? IR1, IR2. So, R1, R2 ratio. If the voltage across R1 balances with L1 and the voltage across R1 plus R2 balances with L2 length of the potentiometer, voltage across R1 is KL1, voltage across R1, R2 is KL2. Then you can say R1 over R1 plus R2 has to be the ratio, K and K cancel, L1 over L2. So, L2 equals this. That is what I explained. Materials and apparatus you need for this experiment: potentiometer, 2 batteries, each 2 voltage, resistors, resistor box, plug switch, two-way switch. Where do we read the resistor box? In the external circuit. If you want to change the current every time, if you want to get multiple readings of L1 and L2, you need a resistor box there. Sliding contact, center 0 galvanometer, large resistance, connecting wires. These are the usual ones that we have used in all the experiments with potentiometer. You know the meaning and use of each of them. Method: arrange the circuit as shown in the diagram. Close switches K1 and K2, open switch K3, connect the two-way switch to R1 only and find the approximate balancing point with a sliding contact. Close K3 also and find the accurate equilibrium point, which is what is going to be L1. Measure and note the balancing length L1. Connect the two-way switch across R1 and R2 and find the balancing length L2 in the same method as above. That is all, getting L1 and L2, right, nothing more. We are not going for a graphical method in this case, but you can go for if you want, but I am not going to go for a graphical method in this experiment. I am just going to take only 2 values, only one L1 and L2 values and get the answer, right. But if you want more accurate answer, you will repeat the same process. Since it is same process, I am not spending too much of time to show that again and again. We can do the same process, get multiple values of L1, L2, draw the graph as well, right. Come, let us see how we can do this experiment now. So, the apparatus required for this experiment are mainly the potentiometer, right. You know how to use potentiometer. We have already used potentiometer in the previous experiments. So, this is a potentiometer. These are the connecting wires. These are the connecting wires, and this is the tap switch. Tap switch, you know how it works. When I touch here, when I tap here, the circuit will be closed. Current flow will happen. When I take my hand out, the current flow will be disconnected. This is the insert key. Insert key, you know how that works. When you remove this key, the circuit will be open, the current flow will not happen. When you close this, circuit will be closed. And then this is another special type of key we are going to use in this experiment. We call it two-way switch. Two-way switch. See how that works. See, when you close it to this side, the wires that are connected to this end and this end, these two ends, you will have two wires, one here, one here. Those two will get closed. Those two will get closed. Similarly, you can have another wire here. So, if you close it on the other side, these two will get closed, right. So, it will be in the middle, right. This, let us say this is one plus wire, this is one minus and this is another minus. Okay. When you connect this one set of wires are getting closed, one circuit will be closed, and when you fold it to the other side, the other set of wires will be closed. I will show you how we are going to use it in the experiment when I am connecting in the circuit. And these are the two resistors, the resistances that we are going to compare these two. We do not know the value of them, two unknown resistances. And this is the high resistance that we use to protect the galvanometer. High sensitivity galvanometer we are using. So, there should not be high current flowing through the galvanometer. It might damage the operations of galvanometer. So, we use a high resistance in series with the galvanometer to ensure high current does not flow through the galvanometer. And this is the battery. You can use this battery, or you can use the Lagrange's battery as well, right. You can use Lagrange's cell or this dry cell as well. This is the galvanometer, sender zero galvanometer. Sender zero galvanometer, it can show you the current flow on both sides, but high sensitive galvanometer. This is the sliding contact, right. We have used this in the previous experiments also. Sliding contact, you can keep it at different points to see at which point you get zero current flowing, that means equipotential point. And then this is the rheostat. We use the rheostat in series with the potentiometer, because from the voltage supply, if you want to get different amounts of voltage to fall into the potentiometer, let us say voltage supply is at 8 volt, the power supply. At one instance, you want 4 voltage to be across the potentiometer. In another instance, you want 5 voltage to be there. In another instance, 6 voltage to be there. Then what do? We connect this rheostat in series with the potentiometer. By changing the value of the resistance on the rheostat, you can decide how much voltage will drop across the rheostat as well as across the potentiometer. That is the rheostat. And this is the resistor box. Resistor box, we will be using it in the battery circuit. Battery, two unknown resistors and the resistor box. They will be used in one circuit. By changing the resistance on the resistor box, you can change the current that flows through the particular circuit, right. And this is the voltage supply, DC, direct current supply, that we will be using, right. This is the direct current supply we will be using. This supply will be connected to the potentiometer and the rheostat circuit. That is all the apparatus required to do this experiment. First, let us see how to make the connection, how to make the circuit to do this experiment. First, let us make the circuit for the potentiometer. See what I do here. You take the positive side of the power supply. Can you see plus here? Plus. Right. The positive side of the power supply, let me connect it to one end of the potentiometer. And the minus side of it, I will not directly connect it. We are going to connect it through the rheostat. I explained you why we need the rheostat, so that we can change the value of resistance on the rheostat, and we can change how much of voltage that falls into the potentiometer. I am connecting it to this port. So, either from this one or this one, I can take the other side of it. So you can see now the rheostat and the potentiometer circuit is complete. I haven't kept or I haven't connected a switch in this circuit because the power supply has a switch. So whenever I want, I can switch it on and switch it off. So I don't need a separate switch. See, this power supply has a switch. You can see. So you can see I can switch it on and switch it off when I want it. Right. So I don't need a separate switch here. That's all in this potentiometer circuit. Then let's make the battery circuit now. This is one circuit, battery circuit is separate, then I will show you how to make the interconnections. Let's make the battery circuit now. To make the battery circuit, I need the battery, the two resistors, and this resistor box. That's all we are going to use there. See the battery, the resistor box, and these two resistors with a switch. We'll have a switch also. All these have to be in series. Let's connect it. Let me take the plus side of the battery. Plus side of the battery and connect it to one terminal of this resistor box. Right, plus side is connected to this. From the other terminal of the resistor box, let's connect it to the two resistors that we want to keep in series. Resistor number 1, resistor number 2, and then after that we have to bring it to the switch. From the switch we will take it to the minus side of the battery. Let's keep the switch open. The insert key, I will keep it open. When I want it, I can close it. Right, there you go. This circuit is complete now. The two resistors in series. I have a resistor box, battery, and a switch. Right? Why do I need this resistor box? By changing the value, changing the resistance in the resistor box, I can change the current in it. So when I change the current, the voltage drop across each resistance will change. Accordingly, L1, L2 values on the potentiometer will change, because you are going to take the same potential difference on the potentiometer also. So current changes means IR1 changes. IR1 changes means here also the length has to change accordingly. Right? So that's what the circuit is. Now see what we do. Let me connect. See now first what I am going to do, let's say this is my R1, resistor 1, R1. So I am going to measure the resistance or the voltage drop across this resistor. The voltage drop across this resistor. Then I am going to measure the voltage drop across both resistors. So what we will do, let's connect the high potential side of this resistor, because current flows through this way. This is where the positive is. Positive goes all the way here. So this is where the voltage is high for this resistor. So the high voltage side of this resistor, I will connect it to, see where I am connecting. I will connect it to the high voltage side of the potentiometer. See again, look at this again. High voltage side of the resistor, where I am connecting to the high voltage side of the resistor of the potentiometer. high voltage side of the potentiometer. Then what I am going to do, concentrate carefully, the potentiometer, the length of potentiometer where the voltage drop across this resistance, voltage drop across the potentiometer string or cable, where that becomes equal, I am going to measure. So what I will do, concentrate, from this point I have to take a wire to this galvanometer, right? These two will be connected. I am not connecting now because I am going to use the two-way switch, but understand, I will connect these two, and then with the tap switch I will search where galvanometer shows me 0 current. Okay, let me just show you for an example now. Look at this. I will just show you for an example. Say from here, let me connect it to the other side of the resistor. So now you can see the galvanometer has been connected here. So the voltage drop across this resistance, look at this carefully, both sides where I have taken, one side has been taken to the start of the potentiometer cable or the string, the other side is through the galvanometer. See, for example, when I keep it here, suppose if galvanometer shows you 0 reading, that means the potential difference between these 2 points and the potential difference between these 2 points must be same, isn't it? Then I can say IR1 equals to K into L1. This length is L, if I say K L1, right? The potential difference, K is the potential gradient, voltage gradient, how the gradient drops. So K into L, that's the voltage drop here. I into R is the voltage drop here, should be equal. Then what I will do, this side will be the same. I will remove this plug or this connection. I will connect it here. Look at this carefully. Both resistors are covered, starting from here up to here. I will connect it here. After connecting it, again I will do the same. See, this point is here. The start of the first resistor is connected here. Now the end of second resistor. So first resistor, second resistor. R1, R2 both are captured. Then let's say at this point if I get the equilibrium, that means I into R1 plus R2, because there are 2 resistors now covered. Look at this carefully. Look at this. 2 resistors are covered. In between these two, there are 2 resistors covered. So I into R1 plus R2 should be equal to K into this length. Let it be L2. This is what we are going to do. But when we are doing the practical, removing the connection and connecting it individually might be difficult. For that, what we are going to do, we are going to use the two-way switch. I'll show you how to use the two-way switch now. I'll show you how to use the two-way switch. Right, we will not be removing and connecting it like this one by one. I'll show you how to use the two-way switch. We'll keep it like this. See, one side of it, I will connect to the first resistor's end of it. The other side of it, I will connect to second resistor's end of it. Right. Then the middle connector, where I will connect that will be connected to the galvanometer. That will be connected to the galvanometer. So see what will happen when I fold it to this side, this circuit will be complete. The galvanometer is connected to this side. Now the two-way switch, if I fold it to the other side, see where the galvanometer is going to be connected, it's getting connected to this end. That is the end of second resistor also. That means this time one end is connected here, other end is connected after both resistors. Can you see from here? Because where the two-way switch is closed on this side. See, this is how the galvanometer is connected. Understand? So, this is how we are going to use the galvanometer. And remember, when you use galvanometer, we have to have a safety resistance. A high resistance will be connected in series with the galvanometer to protect it from high current flow. Let's do that as well. We can't directly give it like this. Let's connect it. Right. Now we can ensure the galvanometer will be protected from high current. On the other hand, after finding the approximate equipotential point, zero current point, then we have to shortcut this. Then only we can find the point exactly, precisely. So, to shortcut that, I'll have another switch there, the tap switch. Right. That's all the connections are. That's all the connections are. Right. Now, we can insert the switch here, the insert key, then the battery circuit will be complete. When I switch on the power supply, the potentiometer circuit will be complete. Right. Then I can close it to my right side. If I close it to this side, then I can find R1, IR1's equivalent length here. IR1 equals KL, the length in the potentiometer string can be found. Then I turn it to the other side. In the two-way switch, I will turn it to the other side. Then I can find the length for R1 plus R2, the total voltage drop among R1 or across R1 and R2. Shall we see how it works? Right, students. Now, let's switch on the circuits one by one. First, let me look at the battery circuit. In the battery circuit, I'll first take 10 ohms resistance in this resistor box. Look at this. This is 10 ohms, 10. Let me remove this plug. Right. Let's make sure all others are tightened. Right. So, now I am using 10 ohms resistance, right. And then the battery from this, the current goes through this 10 ohm and these two unknown resistors, and then it comes through this switch. Let me close the switch now, right. There will be a current flow now. Then let me switch on this power supply as well, right. So, the potentiometer gets the power supply. The two-way switch, first let me turn it to my right side so that only R1 is captured. Only R1 is captured. I explained you earlier how it works. Right. This way, only R1's potential will be measured with the galvanometer. Let's check. Let me keep it here. See, there is a positive side current. At this point is the negative side current. Can you see that? So, in between this point and this point, there has to be an equilibrium point. Let's check here. Negative. Negative. There it's positive. There it's positive. So, positive. See, on this point, negative. Somewhere around this point you get 0, somewhere around this point 0. After finding the approximate point, what do? We have to short circuit this resistance. So, what we will do? We will close this switch, right, and positive side, negative side, still negative. There you go, that is the 0 point, that is the point where it becomes 0. The reading at that point from this side, it's 27.5, 27, from this side it's 27.5. That means, check. Remember, after you get the readings, you have to switch off all the circuits, because two reasons. Through this potentiometer, if the current flows continuously, then the temperature of this, the strings we have in the potentiometer will increase. So that will have multiple effects. One, the resistivity will increase. Sometimes that might get different length after that, that might get elongated. To avoid all that, after you get the readings, you have to switch off the power supply. Also the battery, whether you use the dry cells or whether you use the Lagrange's cell, whichever the one you are using, if you are continuously using that on a circuit, then the potential, the electromotive force of the battery will reduce. So only when you are taking the readings, close the circuits, let the current flow, then disconnect the circuit. Cool. Now from this side we got it at 27.5, which means when you measure from here, look at this, one full length went 100 centimeter, and then from here we got another 27.5. So altogether in 127.5 centimeters we get the balancing point for the potential in first resistance R1, which means I can write I R1. What is I? The current through this battery circuit. I R1 equals K into 127.5 centimeters. 127.5 centimeter. This is the first case. Second case, what should I do? Again, I will close the circuits and change the two-way switch to the other side and find the balancing point. Let's see where it happens. Let me close the circuits. Now the battery circuit is closed. Let's give the power supply to the potentiometer. Power supply to the potentiometer. Right. Change the two-way switch to the other side. Change the two-way switch to the other side. So that now the potential across, or the voltage across both resistance will be captured. I already explained how that works. Let's see at this point, it's a positive current. Can you see? Positive, positive. Still positive. 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 At this point it's negative. Can you see that? It's negative. So in between this point and this point there has to be a 0 point, isn't it? Let's find it. Negative, positive, positive. That's close to 0. That's close to 0. That's very close to 0. You can see that. Now what we'll do, let's short circuit this resistance and find the 0 point. It's plus, minus, minus, a little bit on the plus side. That's the point where you are getting 0 this time. The reading for that one is from here, it's 73 centimeters. 73 centimeters. Let me switch off the circuits. So this time I have taken the voltage difference across both resistors. That means I into R1 plus R2 has been taken. I into R1 plus R2. That is 73 centimeters we got here on the fourth string. That means from here it's 100 all the way. And then another 100, 200. Again I repeat, see, from here it's 100. Second string is another 100, 200. Third string is 100, 300. With the 300, there was a 73. With the 300, there was a 73. So 373 centimeters we are getting for I into R1 plus R2. Right? I into R1 plus R2, we can say K into 373. Now with this, you divide the first equation and second equation. K and K will be cancelled. I and I will be cancelled. You will have R1 over R1 plus R2 equals the two lengths that we have taken. Now I can repeat this experiment again by changing the resistance on this resistor box. When I change the resistance here, what will happen when I change the resistance here? The current will change. The current will change. So when the current changes, IR1, I into R1 plus R2, all that will change. Then I will get different lengths. So I can change the resistance and take different cases. I can take 4 or 5 different cases. For each case I can measure L1 and L2 and I can draw a graph. I will get a straight line graph going through the origin. From the gradient of the graph, we can find out the ratio between R1 and R1 plus R2. From the ratio R1 over R1 plus R2, we can calculate the ratio between R1 and R2. So we will not be exactly finding R1 and R2, but we can get the ratio between R1 and R2. That's what we call comparing two resistances. We can find one resistance compared to the other one. Is it big or small? How many multiples it is? That one we can check with this experiment. Right. So I am going to stop this experiment with one reading. With one reading, I'll do the calculation and get it. But if you want more improved, more precise answers, more accurate answers, you can repeatedly do this, get another 4 or 5 readings, draw a straight line graph, and from the graph, measure the gradient, and you can find R1 over R1 plus R2. Right? So that's all in this simple experiment. Let's see the calculations, how it works. Students, you can see the readings we have got. L1 127.5 centimeter, L2 373 centimeter. Remember the equations we had, R1 over R1 plus R2 was L1 over L2, right. So we inverted it, 1 plus R2 over R1 is L2 over L1. From this you can say R2 over R1, L2 over L1 minus 1, 373, 127.5 minus 1. Let me subtract that also, 127.5. So 5, 12, 7, 5. And then 6, 2, 4, 3, 1, 2. Check that. 6, 3, 7, 3. Correct. I can divide this by 5 up and down, 5, 4, 5, 9, 1, 5, 2, 5, 2, 5, 5, 5, 5. That's it. 491 divided by 255. Divide and see. 1, 255, 6, 8, 5, 3, 2, 236. 9, 9, 5, 45, 4, 49, 4, am I right? 9, 5, 45, 49, 4, 18, 22. That's going to be 65, 650, you will have 2. 1.92 is the ratio we are getting. That means R2 is almost twice of R1, 1.92 times R2 is this many times of R1. So if we know R1, we can find R2, or if we know R2, we can find R1. Clear? So that's a very simple calculation we have regarding this experiment. Now let's see some past paper questions that have come in this experiment. Let's see a past paper question on this experiment from structured essay type questions. This is of 2009 paper. You are asked to use a potentiometer to measure the internal resistance of a voltmeter. Its value is known to be of the order 1000 ohm. The full scale deflection of the voltmeter V is 1.5 voltage. The experimental arrangement that is made for this purpose is shown below. R1 is a suitable fixed resistance and R3 represents the resistance of a resistor box. Let's see. Right. So they have voltmeter here and another resistance R1 here. So like we had R1, R2 earlier, instead of R2 they have the voltmeter. Right. And then the circuit of potentiometer is there. Galvanometer setup is there. This is a two-way switch. Right. What did they say about R1? R1 is a fixed resistance. R3 is a resistor box. R3 is a resistor box. This one, right. What is the importance of having the circuit inside the broken lines marked as Z? This one. Why do we have that? To protect the galvanometer from high currents. Simple as that. We know that why. We have explained that multiple times. To protect the galvanometer from high current. Show how you would connect the voltmeter V to circuit PQRS properly by labeling the polarities of the terminals of voltmeter V with plus and minus in circuit given below. You know, plus of voltmeter has to be connected to the plus side of the battery. So, plus is here, let us put plus here and minus here. The polarities of voltmeter has to be marked. When the circuit is connected, if you observe that the voltmeter readings tends to exceed its full scale deflection, how would you rectify this? Now look at this. Now R1, R2, R3, all three resistors are in series. The voltage, 2 voltage is going to be divided among R1, R2 and R3 according to their proportion. R1 to R2 to R3 proportion, it will get divided. And the voltage that drops across R2 is what voltmeter reads. And it is already given voltmeter's full scale deflection is 1.5 voltage. So, out of 2 voltage, now they say voltmeter tries to show more than 1.5 voltage. It has already gone and hit the maximum side of it. Means what? Within R2, more than 1.5 voltage falls. Let me put some numbers and show it to you. Let us say voltmeter has 1000 ohm. Let us say R1 is 100 ohm. Let us say R2 is at 150 ohms. Now, out of this 2 voltage, how much would be across not R1, R3, huh? Okay, this is what is R2. How much will be across R2? Total resistance is 1350, 1250. R2 has 1000 ohms, so that would be the proportion. How much is going to be? It is going to be, if you multiply up and down by 8, this will become 10,000, 16, 1.6. So, 1.6 voltage will fall into voltmeter, which is beyond its full scale deflection. They are asking now, how would you reduce it? So, how can we reduce it? Either you have to increase R1 or you have to increase R2. But we can't increase R1, they said it is a fixed resistance. So, the option of increasing this is not there. But R3 is a resistor box. I can change the resistance. So, imagine if I increase this to a different value. Let us see if it goes to 350. If it goes to 350, what will happen? Then it will be 2 into 1000 over 1500. So, you get 2/3, which is going to be 1.33. That will be within the full scale deflection. Full scale deflection is 1.5. So, what we can do for the voltmeter to get lower voltage, increase the resistance of others, but R1 is fixed, R3 is what you can change. Let us write it there. Where? How would you rectify this? Increase the resistance R3 of resistor box. R3 of resistor box. Part D. Write down the test that you would perform to check if all components of the experiment arrangement are properly connected. How do we verify potentiometer has been connected properly? Take the sliding contact. touch one end of the string or the wire, your galvanometer will show reading on one side. Now take the sliding contact, touch on the other side, other end of the string. It has to show reading on the other side. Then we know the circuit is okay. Right, I have shown that when we did the experiment also. So let's write it here. Touch the sliding contact on both ends of the potentiometer string. If galvanometer shows deflection in opposite directions, then the circuit is accurate. Next, if the balanced length of the potentiometer wire when the switch T is connected to C and D are L1 and L2 respectively, derive the expression, derive they say, derive, not write down, derive expression L1, L2, R1 and R2. So C and D, first, which one is C? C is when it is only R1 connected, right? So let's say I R1 is equal to K L1. I R1 plus R2 K L2. We will take 2 over 1. R1 plus R2 over R1 is L2 over L1. Right? That's what they asked, L1, L2, R1 and R2. Rearrange the expression in E to plot a graph of L2 versus L1 with L2 as the dependent variable. So L2 has to come to the y axis. L2 has to come to the y axis. L2 will be equal to 1 plus R2 over R1, because we had R1 plus R2 over R1, which will become 1 plus L1. Y equals mx. How would you obtain a set of measurements for L1 and L2 in order to plot the graph? By changing the R3 resistance, you can change the current in that external circuit. That will give you different sets of values for L1 and L2. By changing R3 of resistor box, the current in the external circuit can be changed. This will give different values for, or different sets of values for L1 and L2. More or less directly from the experiment, nothing out of the experiment. You have to think it's all what we have done they are asking. A student has suggested another method to find the internal resistance of the voltmeter V. According to his method, the PQRS section of the circuit shown above is to be isolated and the value of R3 is to be adjusted until the reading of the voltmeter V becomes 1 voltage. Right, see what he is trying to do. Now that PQRS circuit means this one, look at this. You have R1 and this is R2, which is a voltmeter, R2. this is R3, which is a variable resistor. So, change this variable resistor until R2 gets 1 voltage, it shows 1 voltage. So, his idea is this: the battery's EMF is 2 voltage, there is no internal resistance. So, if this shows 1 voltage, R1 and R3 should have got 1 voltage, which means R2 should be equal to R1 plus R3. Why? 2 voltage has gone equally to R2 and the others. So, R2 should be equal to other resistances, right. So, if you know R1, R3 is the resistor box, you know the values that you are using there. So, add R1 and R3, you must be, that should be equal to R2. Not a bad idea, looks good. Let us see. If you adopt this method, write the expression that will give the internal resistance of the voltmeter. Simple, R2 should be equal to R1 plus R3. R2 should be equal to R1 plus R3. Why? 1 voltage here, understand, EMF is 2 voltage. If this shows 1 voltage, other two should have got 1 voltage together. R1 plus R3 equals to R2. Give reason as to why this method is not as accurate as the potentiometer method. There are certain disadvantages in using this method. I will tell you what. First one, you are assuming the voltage the electromotive force of 2 voltage drops against R1, R2, R3 only, and you assume the internal resistance is 0 for the battery. But that can be a theoretical assumption. Actually, the battery also can have an internal resistance. Then out of the 2 voltage, a proportion, at least a small voltage, a small amount would drop into that internal resistance, right. Then the formula will change like this: R2 will not be equal to R1 plus R3 only, it will be including the internal resistance also, which we do not know how much it is, right. So, that is one inaccuracy we have in this experiment, assuming the internal resistance to be 0, point number 1. Point number 2, the resistor box being used there, you have seen resistor boxes, they are available with certain values of resistors only, 1 ohm, 2 ohm, 5 ohm, 10 ohm, it is there for certain values only. Suppose you want to get say 27.75 ohms, the resistor box may not have 0.75 ohms, right. So, R1 plus R2 being equal to R3 or R1 plus R3 being equal to R2, R3 you may not be able to fine tune to exactly make it equal to R2. In other words, you may not be able to get the right resistance to get exact 1 voltage reading in the voltmeter. If it is rheostat, we can do it, because rheostat has continuous range of resistance. Only problem is rheostat, you would know the resistance that you are using. So, that is useless here, because we need to know how much is R3. That is why we are using resistor box. But the problem with that, it is not continuous. It takes some discrete values only. Let us write that. First one, give reasons. First one we can say internal resistance of the battery R may not be 0. Second, R3 can take certain values only, It may not be possible to adjust R3 to get exactly 1 voltage or 1 volt to get 1 voltage exactly on the voltmeter, right. So, those are the general challenges we will have in using this method, clear, right. So, that is a question on this experiment where we compare two resistances. Actually, comparing two resistances, this experiment is no more there in your practicals list, but still I have included that and I have done that for you because it can be still tested, right, in different formats. Even in essay questions this can be modified and tested. So, it is good to know this experiment, it has come in the past, it can be tested in the future also. Practice this, understand it, and then you must be okay with it. All right students, so that is what was there in that exam paper, right. So, now I have done 6 experiments in electricity. I have explained you the theory, have shown you the experimental procedures, and then after that we did the calculations, drawings, got the answers, and we have seen the past papers also, how that had been tested in the past paper questions, right. So, if you can go through all these couple of times, understand and practice this, whatever the questions you get in the exam should be feasible, right. So, practice this, get the maximum benefit in the exams.